So I'm just going to talk about how the internet works, basically from your web browser to a server and back. There are two types of desktop operating systems, Windows and Unix. So speaking of Unix, this is Scott Adams' all-time favorite cartoon that he made. So we're not looking for any Unix programmers. Just want to start with that. Okay, so what happens when you enter canallc.com into your web browser? And I'm going to show you technically, in simple terms, how it works through some demos. So this is the TLDR, too long, didn't read answer. There's 4 steps. A DNS server query will translate the domain name, canallc.com, into an IP address. Your computer then creates a network connection to that IP address, which I'll demonstrate. Your web browser will send a request, HTTP, Hypertext Transfer Protocol, which I'll demonstrate, and then the server sends back an HTTP response. Just to talk a little bit about the protocol, IP means Internet Protocol, and it describes a lot of things, including how a packet is structured and labeled. And it's a protocol, so if you want to send a letter to someone, the protocol for that would be you would write the letter out, you'd fold it up, you would stick it in an envelope, and you'd put the address of the recipient, and you'd put the return address. There's 2 key protocols. There's many, but the 2 key ones we use on the internet are UDP and TCP. And UDP is another name for a datagram, and it's fire and forget. TCP, it guarantees delivery. So you can think of a UDP as mailing a first-class letter. Once you put it in the mailbox, the post office can't tell you where it is or if it's been delivered. TCP guarantees that you know where it's at and you know when it's been delivered. You've probably seen IP addresses. There's version 4 and version 6. Version 4 has the 4 octets separated by the decimal. And about 15 years ago, it looked like we were going to start running out of version 4 IP addresses. So we came up with version 6, which is a lot bigger numbering space. Web browsers will generally connect using TCP IP, and the way they guarantee the integrity of the communication is through a 3-way handshake. And a 3-way handshake is what we do when we answer the phone. My phone rings, I pick it up, I say, "Hello, this is Joe." The person on the other end says, "Hi, Joe, this is Mom." And then I say, "Hi, Mom, how are you doing?" Right? That's the 3-way handshake. We've established a connection. And that's what TCP IP does to guarantee delivery. By way of analogy, we can think, obviously, the internet as a network of roads and bridges and highways, and a packet as a vehicle, like a car, a truck, or motorcycle. And the data is the payload in a packet, just like people, food, and mail are payloads in vehicles. And then DNS is very critical, so I'm going to talk about that in depth. The domain name system is the road signs we see on the road that tell us where we're going and how to get to where we want to go. The first step is a web browser, right? When you enter canallc.com, we need to know the internet address of that server, which is numeric. So let's say we just create canallc.com. We bought the domain and we've created a brand new website. How do computers around the world figure out where the server is that's hosting this website? So after our web browser, after we entered our canallc.com into our web browser, it doesn't know it. So our computer asks or queries our ISP, our internet service provider. It'll query the DNS servers of the ISP for that IP address. Because this is a brand new domain, our ISP has never seen it either. So then our ISP passes that request to probably one of the popular DNS servers. Google has one, 8.8.8.8, and Cloudflare has another one. But again, this is a brand new domain, so we've never seen it. So those servers will forward the request to what's known as the top level domain server. A top level domain, these are the authorities on the .com or the .net, or even some of the obscure ones like .travel. When .travel came about, the first time someone typed that in, even the top level domain servers wouldn't know who the authority is for .travel. So there's this often forgot about service known as the root servers. The internet has 13 fixed root servers that are the overall authority. These are really critical to running the internet. And you probably don't realize, but you'll see when I get into the DNS records, is that all domain names end with a dot. So I'll just give you a quick example of what that looks like. If you're using a proper web browser, I'm using Firefox here. I type http://CANA-LLC.com. If I put a dot on the end and hit enter, you can see the page loads properly, just like we wanted. So that's where we get, we send the queries to. Then we get responses back that trickle down. This is sort of a recursive process. So it walks back up and sends a response back with the name of the authoritative name server, which is also the registrar. Registrars are companies like VeriSign or GoDaddy. And what we get back in this case, as one example, is ns61.domaincontrol.com. And I can show you what that looks like. So here what I'm going to do is I'm going to use a command called dig. This is a Unix command that will dig for DNS information. And all I'm saying here is give me the name server for CANA-LLC.com. And I can put the dot on the end if I want or not, since it's always there. If it's not there, it'll be put in for me. I hit enter and I get back a lot of stuff. Everything here with the semicolon are just comments. It's not actual code that's interpreted by a machine. So this is here just to make it human readable. We get down to the answer section, and here's what our DNS servers see. They see this DNS record or this DNS record. When it comes to domain name system, we always have a primary and a secondary at the very least. And what you're seeing here is this says on the internet, that's what IN stands for, the NS, the name server for CANA-LLC.com, where here it must end in a dot, is ns62.domaincontrol.com. This 3600 is telling the internet that you can cache this information for up to 3,600 seconds, which is an hour, right? If you need to look up this domain again in 20 minutes, there's no need to go back to the authoritative name servers. But after an hour, you need to. Okay, so now we got back. That's how your web browser finds ns61.domaincontrol.com. Then your DNS server asks the domain name registrar, right? Again, that's the authoritative name server, for the destination website IP address. And in this case, CANA-LLC.com, the IP address is 23.236.62.147. And again, what that looks like is we dig. This time, I'm going to put A in there. That means internet address for CANA-LLC.com. And again, right down here, we get back an answer that says on the internet, the IP address for CANA-LLC.com is 23.236, etc. Then your web browser will open a network connection to the server and send a request. And then your browser receives the response back. And I'll show what that looks like. What I'm going to do here is I'm going to establish a network connection. I'm going to use Google because Google just makes for a better example. NC is a tool that you use in Unix for establishing a network connection. I'm going to establish it to google.com, and I'm going to tell it to connect to the Google web server on port 80. There are different ports. They're not physical ports like USB ports. They're just logical ports. But when you connect to a server on a well-known port, which is any port below 1024, if you connect on a well-known port, the server will know what protocol to use. So when I connect to a web server in the clear, meaning not encrypted, I would connect to the web server on port 80. If I wanted to use encryption, I would use port 443, right? And there's a list of well-known ports. So I hit enter, and now I'm connected to the web server. And this is what your browser does. So we have a connection, and we simply want to get the default, that's what the slash means, the default web page from Google using HTTP, and we want to use the 1.1 protocol version of HTTP. So I hit enter, that's one part of the request. And then the second part is I simply say, give me the web page for google.com, because one web server can host many different host names. So I'm specifying google.com. And that's it. I hit enter to send it, and this is what I get back. I get back, this is what your web browser gets. Headers, these are known as headers, and then you get the actual HTML page. And in this case, we have a status code of 301, which in plain English means it's moved permanently somewhere else, right? We're very familiar with 404, which would mean page not found. So where is this moved to? We go to the next line, we see the header location. Instead of google.com, it's moved to www.google.com. Your web browser will automatically, or should automatically, redirect to www.google.com. However, if for some reason that doesn't work, there's a human readable page that will get rendered using this HTML markup that simply says the document has moved, and it puts in a hyperlink, and you can just click there to get to where you want. So let's run this again, and instead of using the host name google.com, we'll use www. So network connection, google.com, port 80. Get HTTP version 1.1, this time though for the host name, www.google.com. And boom, we got back the Google homepage. All this gobbledygook that you're seeing here is obfuscated JavaScript. It's very condensed, and it's JavaScript that's designed to not be human readable. If we scroll up a little, we have a bunch of CSS, cascading style sheets, which give very detailed positioning for words and graphics. But we'll go all the way back to the top, right? Here's my original request. And again, here are the headers, and the status code was 200, which means okay. And what's interesting here is this is how cookies are sent to browsers, right? You can send almost an unlimited number of cookies to a web browser, and this is the information that's stored in your web browser in a cookie. It can be anything. The thing about a cookie, though, is when I send another request, or my web browser sends another request back to the server, the cookies all get sent back. And the reason is that HTML is a stateless protocol. So we need to keep track of the state of things explicitly. And we do that using cookies or sessions on the server. That's how the internet works. DNS is a very important part of it. And I want to stress that that's probably the one way you could take down the internet, because the internet, like I said, is like a bunch of roads. So bombing roads in Iraq would never affect roads in the United States. However, if you wanted to take down the internet, you could take down the root DNS name servers at the 13 permanent IP addresses. There have been 3 attacks like this in the past. The one in 2002 was the only attack that targeted all 13 root name servers, but none of them got through because they weren't using TCP or UDP. They were using another very lightweight protocol that we use for pings that just say, echo back what I sent you. And there were packet filters in front of the root servers. So none of those packets hit the servers. The attack in 2007, it Two of the root DNS servers suffered very badly, and two others, quote, experienced heavy traffic. But again, that was only 4 out of 13. So as long as there's just one that's accessible through this redundancy, we have the ability to look up domain names. And then the last one was in 2015. And in 2015, that was a very big attack against just a few of the DNS servers. And when I say big, I mean to the point that it was almost, or it was 5 million queries per second sent to each one of those DNS servers being attacked. So with that, concludes my presentation. Any questions?
More importantly, the attacks on the DNS servers will affect streaming through Netflix or Amazon Prime. So that's really the most important thing the internet does nowadays, right? If you're watching.
Actually, once you query the DNS server and you have that information, you don't need it anymore. So literally, right, taking down the DNS servers would be like removing every single road sign in the world. If you know where you're going or you had been there recently, you'd still be able to get there, right? If you knew the actual numeric address, you could put that in your web browser. But they're only used for those queries, but there's a lot of steps to get it because you need that like integrity to make sure you end up at the right place.
Yeah, I've got a router here at home that caches all my DNS queries. And so it doesn't have to do that step, and I can get to the pages faster.
Yes.
So like Joe was saying, yeah.
If you visit a site you've never been to before, it takes a moment to load because it's going through all those steps. But then once it's loaded, that's cached. And web browsers are getting smarter and smarter. When you load a web page, they look at every link while the page is loading, or maybe while you're reading the web page, and any domain names that it hasn't visited, it'll sort of warm up the cache and it'll query for that. So if you click on a link that takes you from, say, CNN.com to FoxNews.com, it'll load much quicker.
Cool. All right. Well, thanks. Yeah, it was very informative, and likewise, yeah, that's definitely something that infrastructure in the world now, that if we all went into a time machine about 30 years ago, nobody would think that was important, right? And now it's critical infrastructure. So
yeah, it was a list. It was a list that people passed around like a file, and they said, "Hey, we need an automated way to do this."